Today we're going to be looking at the 2024 paper 1 for triple chemistry higher. Let's have a go. Right, for number 1, full screen. For number 1, it's regarding the reaction of copper carbonate with sulfuric acid. So this is a typical or classic example of the required practical for making salts, which is one of those key important ones for paper 1. All right, so let's go look through. So we have this method is used. So we measure 50 centimeters cubed of sulfuric acid into a beaker, add copper carbonate powder. We're going to stir the mixture, repeat steps 2 and 3 until copper carbonate is in excess. Filter the mixture, warm the filtrate gently until crystals start to appear, and leave the solution to cool and crystallize. Those are key things that we're going to be doing. And as I said, typical required practical, right, that you should know. Okay, now complete the word equation for this reaction. So we have the copper carbonate plus sulfuric acid, and that's going to give 2 products, and 1 is already given for us. So we know that this carbon dioxide is as a result of that carbonate. So every carbonate will produce carbon dioxide, right? If we decompose it, if we react it, it will always produce carbon dioxide as a gas. Now, we know that this is going to be forming salt and water, right, as well. So we know water is definitely one of our products. Okay, now we need to name our salt. Now, I usually go about naming salts based on a first name, last name basis, right? So first name is always the metal, and second name is always based on the acid that is used once you're reacting it with an acid. Okay, so we know that copper is our metal, so that is going to be copper. And we're using sulfuric acid, so that last name is going to be sulfate. Right, so our salt is going to be copper sulfate. Now, obviously, this portion depends on the acid. If we're using hydrochloric acid, it's going to be chloride. If we're using nitric acid, it's going to be nitrate. And obviously sulfuric acid, it is going to be sulfate. Right, so those are the ending. And the first name of the salt is always a metal. Okay, because that's what the displacement reaction is. Because remember, this salt is just the hydrogen in your acid, just the hydrogen in the acid being displaced by a metal. That's what a salt is. Okay, now let's look at the next question. So give one observation the student could make during step 4, which shows that the copper carbonate is in excess, right? So it's in step 4, it says we're going to repeat until it's in excess. What are we going to be looking out for? Okay, so we're going to be observing that solid remaining, right? So we're going to look for that, or you can say no bubbling, right? Because once those bubbles stop, it means that the reaction have now completed and we have no more acid to react with that copper carbonate to form that carbon dioxide. Okay, so that's something else that you could look for in step 4. Now for number 1.3, give one reason for filtering the mixture in step 5, right? So we know that after it's in excess, we filter in step 5, and that is just to remove the excess copper carbonate, right? So we're remove the excess copper carbonate. And that's why we're doing that step 5. Okay. Now let's carry on to the next portion. Right, so 1.4, name the equipment that can be used to gently warm the filtrate, right? And notice that word gently. Okay, and that's a key word. And if it says gently, which is something that we do in when we're making salts, it means that saying something like using a Bunsen burner or using a flame, these are completely wrong, because this does not indicate gentle heating. Right, now what indicates gentle heating is if you say something such as using a water bath, right? So using a water bath, or if you say something like using an electric heater, those indicate gentle heating, right? Now for 1.5, the maximum theoretical mass of the salt that could be produced from that 50 centimeters cubed of sulfuric acid is 12.5 grams, right? So we know that this is a theoretical mass, right? The percentage yield of that salt is 92.8. Calculate the mass that we can actually produce. We're going to use the equation. So because it gives us the equation, we're just going to input things into this equation before we rearrange. So it gave us a percentage yield, which was 92.8, and that's equal to the mass of the actual salt. We do not know that, right? So that's the mass of salt that is produced. We don't know that. We're dividing it by the theoretical, which they gave us as 12.5, and then we're multiplying that by 100. Okay, so that's our setup. Now all we need to do now is rearrange that equation to find the mass produced. Okay, so mass produced is equal to that 92.8 divided by 100, and we're multiplying that by 12.5, and that's going to give you an answer of 11.6 grams. Right? And that's a simple 3-marker calculation question. It gave you the equation, so all you needed to do was to just input those values, rearrange, and solve for that. Solve that question. Okay. Now, question 1.6. So some salts can be produced by reacting sulfuric acid with a metal. Neither copper nor sodium is used to produce a salt with that sulfuric acid. And we're going to give one reason why each of these metals, they cannot be used. They're not used when we're producing those salt, right? And if we're thinking about these, we're thinking about the reactivity series, right? So we know that sodium is somewhere at the top and copper is at the bottom, right? And we know that based on the reactivity series, as we go down, it becomes less reactive as we move down the reactivity series. And we also know that hydrogen is somewhere here, right? Which means, therefore, that copper is unable to displace hydrogen. And if it's unable to displace hydrogen, it means, therefore, that it will not react with the acid, right? Because remember, we mentioned this before. In order for salt to be produced when you're reacting these with acid, it means that the metal must be able to displace the hydrogen. And if it's unable to displace the hydrogen, a reaction will not take place. So we can say for copper, it does not react with acid. And that is our reason why we could not use copper metal by itself, right? That displacement will not happen. Okay. Now we can see that on the other hand, for sodium, there is a chance of displacement because sodium is more reactive than your hydrogen, right? However, because sodium is very, very highly reactive, it means that it could get explosive. Right? Or you can say the reaction is dangerous, right? Any one of those would suffice, right, for this reaction. This is about the periodic table. So we have sodium and potassium. These are both in group 1 on the periodic table. And I have the periodic table right here just for your reference, right? And we can see that in group 1, we have the sodium. We also have potassium in that group. And it's asked for us to give one similarity and one difference between the electronic structure of potassium and sodium. So we're going to look at the electronic structure. Now, let's just write the electronic structure for a second here, right? So for sodium, it's going to be 2 in the first shell, 8, and then 1 in the last shell. And for potassium, it's going to be 2 in the first, 8, 8, and 1. So that's the electronic structure for each of these. And we can see it conforms with what we have here, right? Group 1, they both have 1 electron in that outer shell. right? And then we have sodium being in periods 1, 2, 3, so which means it has 3 shells. And we have potassium being in period 4, which means it has 4 shells. Okay, so now using that electronic structure information, we're going to state give one similarity and one difference. So one similarity, so we can mention they both have 1 electron, both have 1 electron in outer shell. And the difference, we can see that the number of electron shell for each, they're different. So we can state that as a difference. So we know that sodium has 3 shells, while potassium has 4 shells. Right? So now we have one similarity, one difference for each of them, and it's based on their electronic structure, nothing else. Okay, now for group 1 elements react with water, we're going to give 2 observations that can be made when potassium reacts with water. Okay, now if you remember, because this is usually a demo done by your teacher, right, where you have your trough that contains that water, so that's my water, and they add small bits of either the lithium, the sodium, the potassium to the water, and you're observing what's going to happen, right? Now, if I should put potassium in this water, right? So I'm putting potassium in there, right? Now, the first thing I'm going to observe is the fact that you're gonna be floating on that water. So we can mention that as an observation. So it floats, right? We are going to observe that. We're going to see some bubbles, so we can mention that as well, right? So bubbles, please do not write that a gas is produced, because if you write a gas is produced, that is not an observation, right? So in order for us to know that a gas is produced, we're going to observe bubbles or fizzing, right? Bubbles or fizzing, that's the observation if a gas is produced. Okay, you can also mention that it's going to be moving around, because it's usually moving around on the surface of the water, right? So move around. And one key thing that usually happens with potassium is that it is going to form a flame. We're going to see a flame. You don't need to mention the color of the flame, but we know that a flame is going to be there, right? But if you mention the color of the flame, that's ignored. So all you need to mention is that there will be a flame, a lilac flame, right? If so, right, that will give you the mark nevertheless. Okay, now for number 2.3, we have potassium hydroxide solution is produced as potassium reacts with water. What is the color of the universal indicator when added to potassium hydroxide solution? Right, now we need one reason for this answer. So the color is going to be, we know that all the metals in group 1, these are called alkali metals, right? They're all called alkali metals, and that's because they form alkali solution, right? So when we add universal indicator to it, you should be getting a purple color, or if you have blue, that is acceptable as well, right? Now, the reason for this is because the solution is now alkaline, right? So solution is alkaline, right? So all your group 1 metals, everything in group 1, right? These are going to form alkaline solution, right? Once you have placed them in water, right? And that's why they're usually called alkali metals, right? Now let's carry on. Now for this one, it shows us a bit of the trend in terms of the densities of some elements that are in group 0 of the periodic table, right? And group 0, we know those are the noble gases, the royals of the periodic table, right? So we have our helium all the way to radon. It gave us the atomic number, and we can see that as we're moving down, atomic number increases, and that corresponds with the trends in the periodic table. And once we're looking at the density, we can also see that as we're moving down, the density is also increasing as well. Okay, now the first thing here is for us to plot the data from table 1 onto figure 1, right? So let's see if we can quickly plot this on in table 1. So this is what your graph should look like somewhat. My line isn't as straight as I want it to be because I'm using a freehand really, but yours should look a bit better than mine is right now. Okay, so let's move on to the next one. So 2.5, it says we're going to estimate the density of krypton using the figure and the table. Now we're going to just use the figure to do this. So it says the atomic mass of krypton is 36. So all we need to do, I'm just going to zoom in on my graph. All right, let me quickly zoom in on my graph. And from my graph, I'm going to look for 36. So 36 is along here. Let me change my color pen. This is 36. So this is 30, 2, 4, 6. So 36 is along here, right? And if I should go across, I am going to be somewhere about 3.246, 3.6. Right, I'm going to be at 3.6. So I know that the estimated density based on my graph for krypton is going to be 3.6. Now, obviously, this is an estimation question, which means there will definitely be a range of values that you can get for your correct responses. So that's going to be 3.0 to 3.8. So anything along this line you get for that estimation, that's absolutely correct. Okay. Right. And you're just using your figure. Using your figure, you're absolutely fine with just estimating it from the line of best fit that you have drawn. Okay, now for 2.6, right? The elements in group 7, these are called the halogens, right? So more reactive halogen can displace a less reactive halogen from a solution of its salts. The classic definition for a displacement reaction, really, where a more reactive can displace a less reactive one that is in solution or within a salt. Which combination of solutions will produce a reaction when they are actually mixed, right? So this is our halogen. So we have our chlorine, bromine, iodine, astatine. Okay, so these are our halogens. Now, as we move down the group, it becomes less reactive. Because remember, our halogens, they're electron loving. So they love electrons, so they will attract electrons onto themselves. So the further down we get, the bigger the atom will be, so less chance of actually attracting those electrons. So fluorine is small, then as we're moving down, it gets bigger and bigger, which means the ability to attract that electron, it becomes less likely to happen the further down the group we actually go. Okay, so now let's look at which combination would actually reap a reaction. So we have chlorine reacting with potassium fluoride. Okay, so we're comparing the chlorine and the fluoride in this case. So fluoride is more reactive, so it means that this displacement reaction will not be happening. Chlorine is not as powerful enough to displace that fluorine. Okay, now the next one, chlorine and the bromide. So let's look at this one. So we have chlorine and we have bromide. We can see that chlorine is more reactive, which means that is going to be our answer. Okay, so that is more reactive. So we will have a displacement reaction taking place if we react chlorine with potassium bromide. For 2.7, which of the following describes the trend going down group 7? So as we're moving down group 7, and this trend is regarding the relative molecular mass and the boiling point. So that's what is regarding. So let's look at the relative boiling point. So we know we're going down the group. Okay, so as we're moving down the group, we know that the relative molecular mass, that is going to increase. So we know that as we're moving down the group, relative molecular mass increases going down. So now we need to find out what is happening to the boiling point. BP, sorry, not BB. What is happening to the boiling point? So we know that as we move down the group, electron density also increases. So if we have increased electron means increased intermolecular force. And if the intermolecular force increases as we're going down the group, it therefore means that we're going to need more energy to actually melt or boil or do anything to this structure. So as we're moving down, if the intermolecular force increases, it also means that the boiling point will also increase, right? So this is the one that will agree with everything that we have said. So relative molecular mass increases, so the mass of that molecule increases as we go down, increasing in that molecular mass, also synonymous to the increase in the electron density, which increases that intermolecular force. So it means that boiling point will also increase as we move down that group as well. Okay, so boiling point increases. So these are our key things for this one. So for question three, this is about the models of the atoms. So for figure 2, it shows 2 of the early models of the atom. So model A, we can see that ball of positive charge, and we can see those negatives. For model B, we can see that that positive is in the middle, and we have those negative charges around the structure. Okay, so the first thing it asks us for is to name the models of atom shown in figure 2. So the famous model, which is a ball of positive charge, that is the plum pudding. The plum pudding. If you want to say the Thomson model, that's fine as well, because J.J. Thomson is the one who coined this model for the atomic structure, right? So model B, that is a nuclear model, the nuclear model. If you want to say it's the Ernest Rutherford or Rutherford-Bohr model, right, that is fine as well, right? But this is the nuclear model, the most modern model of the atom. Okay, now we're going to compare model A with the model of the atom used today, right? So we're looking at model A, which is the plum pudding, and the model that we use now. So we're going to be comparing, and you should know that if you're comparing, it means that we're going to be looking at similarities and differences. Right, so that's what we're going to be looking out for when we are comparing these two models. So it's the plum pudding model and the current model that we use to draw these structures in today's time, right? So first, let's look at the similarities, right? So for the similarities, first thing we can mention is the fact that they both contain electrons, right? So both contain electrons, right? We could also mention that both are neutral, because all atoms are neutral overall, right? So both are neutral. And that's something else that you can mention. I think those are the only two similarities, to be fair, right? So now we can move on to differences. So for differences, now we can focus on those intricate details. Okay, so for model A, we can see that model A does not have a nucleus. So that is something that is very different in terms of the plum pudding model and the one that we're using today. So we have model A, no nucleus, right? While the current model, it does, right? It has no protons. Model A has no protons. Protons, not sure what I'm spelling there. has no protons. Model A, neutron was not discovered as yet, because remember, neutron was discovered by James Chadwick, and during the discovery of the plum pudding, we could not have discovered those neutrons, right? So model A, no neutron, right? Because that was not discovered as yet. Right? So some other key information is the fact that for model A, the electrons are randomly distributed. So model A, electrons are randomly distributed, while on shells for modern model. So that's a key difference. Another key difference for model A has no empty space, while the modern model is mostly empty space. Right, and you should remember this based on Ernest Rutherford's gold foil experiment, where the alpha particles, and you notice few observations that most of it is full of empty spaces because most of those particles went all the way through, right? Some of it is the positive charge is concentrated in the middle because of those deflection that happened, right? So you should know those ahead of reviewing this. So that is something that you could look at as well. Okay, so these are some similarities and differences between the plum pudding model and the modern model. Okay, so you can mention these. Another one, based on the observation from Ernest Rutherford's experiment. So model A was spread out. Mass, but A is mass. Sorry, was spread out throughout the structure. While modern model is concentrated in the nucleus. Right? So those are a lot of differences that you could have pulled on for that 4 mark. Okay, and this is a leveled response, which means having those similarities and differences is literally crucial in actually gaining that level 2, that top end of the marks, that 2, 3, and 4 mark. So yeah, you have a wealth of information here that you could use. Sorry about the mess. Hope you could follow it quite nicely. Now for 3.3, Chadwick's experiment showed the existence of neutrons in an atom. This led to the understanding of isotopes. Now, define the term isotope, and in this, we are going to refer to the subatomic particles, right? And notice this, whenever you're defining isotopes, you must refer to the subatomic particles in order for it to be correct. Okay, so if you refer to atomic number or atomic mass, then it is going to be incorrect. If you refer to these, it's going to be wrong because it explicitly states that you should be referring to the subatomic particles. Okay, so this is atoms with the same number of protons. Notice I'm using proton, a subatomic particle, same number of protons, but different number of neutron. All right, and notice I'm using those subatomic particles, the protons, the neutrons. Those are the ones that you're going to be referring to, and those will give you the marks for your definition for isotope. For question number 4, this is regarding energy changes. So a lot of these required practical scenarios from energy changes is always using a thermometer, determine if something is exothermic or endothermic, right? So that's usually the case with energy changes, right? So key thing, thermometer, and you're looking out for temperature change. Decide if something is endothermic or exothermic. So this is between zinc and copper sulfate solution, and in this experiment, you use this method. So they measured 25 centimeters cubed of copper sulfate solution in a polystyrene cup. That polystyrene cup is quite important. So measure the temperature of the copper sulfate solution, and then you're going to add 0.2 gram of zinc powder to the copper sulfate solution. Stir that mixture, record the highest temperature reached, and you're going to repeat steps 1 to 5 using different masses of the powder. So this is what the result shows. So this figure 3, it gives you the results that have all the highest temperatures that were achieved using those particular masses of the zinc in your copper sulfate solution. So the first question for question 4, it says to draw 2 lines of best fit. So again, 2 lines of best fit, and I'm going to underline that. And we should ensure that the lines actually cross. That's something that is quite important. And because it states that, it means that one of those marks will be for that line crossing. So let's see if we can draw this. Now, I don't have a ruler, so I'm going to do this as best as I can, right? So I'm drawing my line of best fit. Use your ruler. So the first one would have the first 5 points, and I'm drawing it longer than where it ought to be to ensure that it crosses. And then I'm going to draw the line for the next bit. Now notice I'm not including that anomalous point. So this anomalous point, I'm not including that in my line of best fit. Okay, so I have my line, and I've also ensured that it has crossed each other at that particular point. Okay, so let's look at the next question. So I've done question 4.1. Let's look at question 4.2. So explain the results shown in figure 3. Do not refer to anomalous points. Use data from figure 3. So explain. This is an explain question, which means when I'm doing so, I must include 2 keywords. So this must include either because or so. So either of those must be involved in my explanation. And it also says use data from figure 3. So I know that I must use some specific information from that figure in order for my answer to be supported. So now let's look at what we could say for this. So let's explain the first bit. So when we're looking at the graph, we can see that the temperature is rising. So as the first thing we can see, so that temperature rises, right, as we're increasing the mass of zinc added to that copper sulfate solution. So why would that be rising? Because it is exothermic. So we know that temperature rises because the reaction is exothermic, right? But we know that, let's go back to the graph for a bit. So we know that it rises, we can see that rise. So we can see that rise happening here, but it stopped rising. So it rose because it's exothermic until approximately not approximately, it's definite because it's smack on the line. 0.8 grams of zinc is added. So it rises because it's exothermic until 0.8 gram of zinc is added. And that's data from our figure, right? So we've used data from our figure, right? But that's just the first portion of our explanation. So we've explained only the first portion here. Now we need to explain the next portion, this portion here. So after 0.8 grams, after 0.8 grams, there is no additional rise in temperature or reaction. Because of what? Remember, we're explaining why did this happen, right? Because zinc is in excess. Right? You could also write that it's because the copper sulfate solution was all used up, right? So you could also mention because copper sulfate solution is used up. Because once this happens, it means that no more reaction will be taking place, right? The temperature will no longer be increasing any further. Reaction have completely stopped. Okay, so that is our question 4.2. And please remember this key command word when you're using because. When you're explaining, you need to be using that because, that so in your response. That is given a reason for something happening. So the temperature rises, we can see that. Why did it rise? Because that reaction is exothermic. And we're including that detail from the figure until about that 0.8 gram of that zinc is added. Or if you want to put that maximum temperature, which was around 47 degrees Celsius in place of the mass, that's absolutely fine as well, as long as you're using information from that figure to support your explanation. Now for 4.3, explain why using polystyrene cup gives an accurate result than using a beaker. Right, so this is a classic case for this required practical. Why is it that we use polystyrene cup? So polystyrene cup, we know that it's a better insulator. Polystyrene is a better insulator. And if it's a better insulator, it means therefore that less energy is transferred or wasted to the surrounding or lost to the surrounding, right? So less energy lost to the surrounding. This means the temperature that you record on that thermometer, it is close to being accurate because most of that heat isn't being dissipated into the environment. It isn't being lost to the environment. Okay. So question 4.4 is to complete the ionic equation for the reaction between zinc and copper sulfate solution. And again, this is a classic case of displacement reaction. We're more reactive, so more reactive is displacing the less reactive. This takes us back to the reactivity series. Right? So we have copper, which was in solution. That's why this is aqueous. It was in solution. We added that zinc metal, and because zinc is more reactive, it is going to take the place of copper in solution. So which means that we're going to have that Zn 2+, and because it's 2+, we know that's going to be aqueous because it's now in solution. And then we're going to have copper, and that's going to be solid because it was displaced. All right, classic case of displacement reaction. Right. So for the next bit, so we have a difference unit repeated steps 1 to 5 of the method 4 times using 0.5 gram of zinc powder. And the results are shown in this table. So we have all the highest temperature reached based on 4 different trials. It says we should calculate the mean of the highest temperature reached, and we're going to include uncertainty in our answers. Now, if we're looking at these, I know that the case is usually you calculate the mean and leave the anomalous point. You do not include that in your mean. But if we're looking at these points, we notice that they're all over the place, really. So we're going to use all of them to calculate the mean. And then we're going to use our uncertainty to see where within this region does our actual result lie, right? Considering that it's all over the place. So we're going to be using our 37.6 plus 37.2 plus 37.8 plus 37.4, and we're dividing that by 4. So that's going to give us a value of 37.5, right, degrees Celsius. So that we know that the maximum is going to be 37.5. Now we need to find the uncertainty. Okay, so to find uncertainty, and if certainty, sorry, I was spelling that incorrect. Now, to find the uncertainty, that is the range divided by 2. And we know the range is just the max value minus the minimum value, and you're dividing that by 2. So our max value in this case is going to be 37.8 minus our minimum value, which is 37.2, and we're dividing that by 2. So that's going to be 0.6 divided by 2. So we know that our uncertainty is plus or minus 0.3. That is going to be our uncertainty for this calculation, and that will give you your full 3 marks. Now for 4.6, the result shows random errors. The student did not make any measuring errors. So just one reason that a random error could happen in this experiment. And for your random errors, these are things that just happens, like you did, it just happened. As it says, it's random. So one such thing that could potentially happen, maybe for each of the trial, the starting temperature was different each time. So obviously you're going to be ending up with a different highest value if the starting temperature changes each time. Okay, so starting temperature differs for each trial. That's something that could happen, right? Inconsistency in stirring, because they're not using an electric stirrer where you can set the pace and it's the same for every single one. It's manual stirring, which means therefore you're not going to be doing it at the same pace at all times, right? So inconsistency with stirring. It could also be inconsistency with the use of the lid as well, right? So inconsistent use of lid is, again, you're manually placing the lid over once you've added the zinc solid. So the time it takes for you to do that each time, it will differ, even by a few seconds, right? It will differ. So that could also lead to some of that heat being lost to the environment before you put that lid on, which could affect that maximum temperature. Okay? So that's something that could potentially happen, right? So question number 5 is about electrolysis. Now, electrolysis, this is a topic that is not well loved, but it's quite simple. It's quite a nice topic. So electrolysis, as it suggests, electrolysis, means electricity, not electro. And the lysis portion means to break down or to decompose. So if we're putting that in a definition, so this is using electricity to break down ionic compounds. And bear in mind, these ionic compounds, it must be either molten or liquid, or aqueous means it's dissolved in water, because those ions need to be mobile. They need to be able to move about freely in order for this process to take place. So we're just using that electro to break down an ionic compound. And in this case, the ionic compound is calcium chloride. right? Now, for this, it mentions that we're going to be describing what happens to the calcium atom and the chlorine atom in order for this ionic compound to be formed. So I'm just going to do this quite simply, right? So let's focus on calcium first. So we know that calcium is in group 2, which means it's going to lose 2 electrons. That's key information. And we know that chlorine is in group 7. So it's gonna gain 1 electron. Now, this is going to react. In order for this reaction to take place, we need to figure out the ratio at which this will happen. And we can see that based on this, we're going to need a ratio of, this is it, so calcium to chlorine ratio. So we're going to need 1 calcium. That's going to donate 2 electrons. So it means, therefore, we're going to need 2 chlorine so that they can accept those. Because remember, each of these chlorine will only accept 1 each. So the follow-up for this question is the fact that 1 calcium will react with 2 chlorine Cl atoms to form Ca2 plus ion and Cl minus ion, 2 Cl minus ions. So that's what's going to be happening in this reaction for us to form that calcium chloride. So notice the group. Use your periodic table to support you. Once you know how to use that periodic table, it can help you a whole lot with answering these questions. So we know group 2, lose 2 electron. Group 7 is a non-metal, so it's going to be gaining, and it needs 1 electron, so it's going to gain that 1. So we need a 1 to 2 ratio in order for a reaction to take place. 1 calcium, 2 chlorine atoms, and then that reaction will form those ions, that Ca2 plus ion and 2 of those Cl minus. If you just have Cl minus, that's absolutely fine as well. You don't have to have 2 of Cl minus. So that's absolutely correct if you only have the Cl minus by itself. Now for 5.2, solid calcium chloride cannot be electrolyzed. And remember, we said it at the top up here, where the ionic compound, it must be either liquid or aqueous. So why is it that the solid cannot conduct? And that is because the ions, they cannot move. They're fixed in position. Right? So ions are fixed in position. And if you go back to, well, I think this is key stage 2, key stage 3, when you're drawing the structures of solid, liquid, and gas, right? Remember that solids, they're always fixed. They're fixed in place, which means they're just vibrating. So this cannot move about in order for electrolysis to take place. Okay? But if it's in the molten form or the aqueous form, then those ions are free. They can move about. And that's what is required for electrolysis to take place. Number 5.3, name the product formed at the negative electrode when aqueous calcium chloride solution is actually electrolyzed. Now let's look at, I'm just going to draw my electrolytic cell. So this is my electrolytic cell, right? I have my electrodes in there, and I have my electrolyte. So my electrolyte, I know that it's going to be calcium chloride, and it's a solution, so that is aqueous. So one thing I need to note, because this is aqueous, it means therefore I'm going to have several ions in there. So I'm going to have my Ca2 plus ion, I'm going to have my Cl minus ion, and the aqueous suggests H2O. So, suggests H2O, which means that I'm also going to have the ions from water, which is H plus and OH minus. Okay, so this is asking about the negative electrode, the product formed at the negative electrode. And I know without a shadow of the doubt, because opposites attract, my negative electrode will have these going towards it, right? So those will go towards my negative. Now I need to determine which is preferentially discharged. Now, based on the rule, it says if it's more reactive than hydrogen, it means that hydrogen is going to be produced. So it's the less reactive. Let me simplify the rule. Less reactive in the reactivity series will be produced. That's a simplified rule. So it means that if I'm looking at my reactivity series, I know potassium is at the top, calcium is somewhere here, hydrogen is somewhere down here. I can see that hydrogen is less reactive. So it means that that product at my negative electrode is going to be hydrogen. I'm using the wrong color. It's going to be hydrogen that is going to be produced there. Right, so you can write the word. If you have H2, that's absolutely fine as well. Okay, so that's the rule at the negative electrode. Once it is less reactive in that reactivity series of metal, then it is going to be preferred. It is going to be produced. Okay. Now, number 5.4, what is the half equation for the reaction at the positive electrode when aqueous calcium chloride is actually electrolyzed? Okay, now let's look at this electrode. So at the positive, we know that these will go towards the positive. Now we need to look at the rule at the positive, and the simplified rule. See if I can use a different color. So the rule, simplified, I'm going to simplify it as best as I can, right? If a halide is present, it is produced. Sorry, again. It is produced. All right, so if a halide is present, it is produced. If not, OH minus is preferred. That's a simplified rule. So looking at each of those ions at your positive electrode, if you see a halide, so that's your fluoride, chloride, bromide, iodide, acetate, any of those, if you see them, chances are you're not going to get acetate, or chances are you're not going to get that. But if you see any halide, that's preferred. But if there's no halide, then it means, therefore, it's going to produce that OH. So you're going to be seeing that bubble confirmatory test used for oxygen at that positive electrode. So that's a simplified rule that you need to know. So if I'm looking at this now, I can see that there's a halide present, Cl minus. So I know that in my question over here, I am going to be looking out for just my Cl minus, and I'm going to check which of those is correct for my Cl minus. Okay, so let's see. So we have our Cl minus, and we know that this have lost an electron already. Gained an electron, sorry, it's gained an electron already. So in order for us to go back to being the atom, we're going to do the opposite. So now it's going to be losing it. So this suggests that we're adding the electron on to the Cl2 to form our ion. That is completely wrong, because in electrolysis, we have our ion trying to form the atom. It's literally the reverse. So we have our Cl minus, and it's going to form our chlorine gas plus our 2 electron, because it's now losing those electrons that it had, so that it can go back to forming its atom. And remember, it's diatomic, so that's going to be Cl2. Another way of writing this equation, if you see this equation like this, so 2Cl minus 2 electron giving you Cl2, right? This is also correct as well, right? If you write it like this, is also accepted at GCSE, so you can use it like that as well. Okay, so that's our answer for this one. Please remember those rules at your positive and your negative electrodes. They will help you to answer these questions. 5.5, a student investigated the electrolysis of green copper chromate solution. So this is the apparatus. So we can see in our apparatus, we have our power supply, we have the negative rod, we have our filter paper, which is soaked in an electrolyte solution. And then we have our just a drop of that green copper chromate solution. Now for the results of figure 5, it showed that the blue color is drifting to the negative electrode. But in your mind, you should be thinking it's copper chromate, which means that copper is usually blue. So it simply means that this must be Cu2+. That must be copper. And it means that this must be the other thing, which is the chromate. So that is your CR04. That's going to be your chromate. So it says copper chromate solution, it contains those two ions, and I've written those two ions already. Right, so explain the results that are in figure 5. So let's look at this results, and I've already given you a hint as to what that result would look like. So we have the Cu2+, that is blue color. Cu2+ is blue, while the chromate is yellow. So we can see that, right? And we've noted that down. So rule of thumb, you've worked with copper sulfate, right, and copper compounds a lot during practicals. Always remember that copper 2+ is blue. And you would have known this from your qualitative tests, right, that you would have been exploring for the content for paper 2. Now, Cu2+ is going to move towards a negative electrode, and we can see that on the image. So that Cu2+ moves to negative electrode, and our chromate moves to the positive electrode. And use number 6 is about a student who investigated the voltage produced by different pairs of metal electrodes in a chemical cell. So these chemical cells, these is literally just used in a reaction just to generate a voltage. Okay, so the use of a chemical reaction to generate a voltage or potential difference. Okay, so that's what we're doing here. So based on this experiment, it says they placed a nickel electrode and an electrode made from different metals. That's electrode A. So this is made of various different metals in 1 mole per dm cube solution of sodium chloride. So they measure the voltage produced and they repeat it with different metals in the position where electrode A is. Now these are the various metals that were used in place of electrode A. So we have the copper, magnesium, nickel, silver, and zinc. Now obviously nickel is used there. So it means, therefore, if we use nickel again as electrode 8, that's going to give 0. They're literally the same metal. So there will be no transfer of electron from one to the next. And this takes us back to the the reactivity series of metals, where we have the most reactive at the top, least reactive at the bottom. And that's what we're going to be looking at this. We're going to be ordering them. So you should know that the most reactive metal, that is usually a metal with the highest voltage, the more positive voltage. So if I'm going to arrange this, I'm going to look at the more positive. And in this case, it's going to be magnesium. So magnesium is the more positive. Then in line, we're going to have zinc. Then we're going to have nickel, because nickel in that case is 0. So that's the middle ground there. So that's Ni. Then we're going to have am I looking? Silver. And then we're going to have copper. So that's what the structure would look like. And the reason for this, because we need to justify this, let me just write these on the line. Mg, zinc, nickel, silver, and copper. Now our justification is the fact that the more reactive a metal is, the higher the voltage will be. So that's our justification. More reactive metals have the highest voltage. And that's our response. And by highest, I mean the more positive of the lot. Number 6.2. So the voltage produced by a chemical cell depends on the concentration of the electrolyte solution that is actually being used. We're going to plan an experiment to investigate how the voltage produced by a chemical cell varies with the concentration. So by this, we know that concentration is our independent variable. So that's our independent. This is what we're going to be changing, which means that everything else we're going to try and keep the same in order for us to make it a fair test. So in order for us to investigate this, they gave us a few substances that are available to us. So we just have metal electrodes from table 3. And because we know our independent already, we know that the metal, we are going to be keeping this the same. So this is going to be controlled variable. So we need to ensure that we select 2 metals from the table above, and we keep those the same. So if we're using magnesium and zinc, we're using magnesium and zinc for all the experiment when we're changing the concentration of the electrolyte. Nickel and silver, we're using those for all of them as well. Okay? And we have pure water, and pure water is there for the dilution factor, right? To dilute, right? So that's the purpose of that. So we're using that to dilute that 1 mole per dm cube solution so that we can have that varying concentration. So that's the purpose of it. Now let's see if we can write our method. Okay? So the first thing I'm going to do, I'm going to set up my electrolytic cell, right, using my sodium chloride solution, the one that I've been given. So 1, set up cell with sodium chloride solution as the electrolyte. The first thing I'm going to be doing, and that is the 1 mole per dm cube sodium chloride solution that we're talking about. Okay, the second one, use 2 different metals for the electrode. Right, I'm going to put a note there. Ensure to keep metals the same for each experiment. So that's just a note to my examiner that I'm going to keep the metals constant. I'm not going to be adjusting those. Okay, so number 3, I'm going to measure the voltage. Measure the voltage, right, of the electrolytic cell, of the chemical cell, sorry, chemical cell. Step 4, I'm going to repeat with different solutions. Repeat using varying concentrations of the sodium chloride solution. And ensure to use pure water to dilute the sodium chloride solution while keeping the volume constant. Right, so in this case, we are telling how we're going to be using that pure water, and we're also mentioning that volume, it must be kept constant because that's going to be a control variable as well. Because remember, the independent variable is concentration. That's all we want to affect. And if we alter the volume, it means therefore that we are also changing volume as well, and we don't want to do that. Okay, so can follow up by mentioning, you could also include, they're going to be using a measuring cylinder. Use measuring cylinder. To get accurate volumes, right, in your measurement. So that's something that you could include. So this doesn't need anything more than this for this practical. You've explicitly stated exactly what's going to happen, right? Using this practical, you can get those valid results. So you're going to set up that cell. You're going to use those two different metals. You're going to measure the voltage of that chemical cell. Then you're going to repeat it with varying concentrations in which you're going to be using that pure water to dilute, ensuring that the volume is constant. You're going to be using that measuring cylinder to get that accurate result. Now, if you want to be even more accurate, you could also mention, instead of the measuring cylinder, you could have mentioned that you're going to be using the pipette instead, right? So the pipette, you could mention that as well. Guys, I've forgotten how to spell pipette now. So you could mention that you're going to be using a pipette instead, which is more accurate than the measuring cylinder. Okay, but that's all you need to have for this question. It's not a really difficult one, right? It's just for you to put those key things together, ensuring that in your method you've identified what you're going to be controlling, what you're going to be measuring, what you're going to be changing. Just having those set in this method. All right, this was a very decent 6 marker, very nice 6 marker. Okay, so question 6.3 is about hydrogen fuel cell. So we're going to describe how a hydrogen fuel cell produces a potential difference. So if you remember hydrogen fuel cell, you remember that I'm going to try and draw this out now. Oh, that's colorful, right? I'm not the best artist, right? So for our hydrogen fuel cell looks something like this, right? So we have, let me just finish drawing these out. Now we have our voltmeter around. Okay, so we have hydrogen being pumped in at this end, right? And it is usually oxidized. So we know that hydrogen is going to be oxidized. And if you remember, oil rig, right? So oxidized hydrogen is going to be losing those electrons to form H+. So that's 4H+. And those 4 electrons, they are going to be moving around. Right? They're going to be moving around to your cathode. So this is your anode, to your cathode, where you will have your oxygen, O2, being pumped in from the air, and that oxygen is going to be reacting with your H+, your electron, and then it's going to produce water, right? So that's the aim of this. So to answer this question, it's just mentioning that your hydrogen is oxidized. I'm spelling that wrong. Is oxidized to form water. Right? If you have that loses electron, right, to form water, then that's absolutely fine as well, since oxidation by definition is a loss of electron. Okay, so at your anode, you're going to be having your H2. You're going to be having your H2, and that's going to be forming your 4 electrons plus 4 H plus, and this H plus, that's the one here, and the electron will be passed through the wire around the circuit to your cathode. Right, once it's at the cathode, you're going to have your O2 plus your 4H plus your 4 electron, and that's going to be forming 2 moles of H2O. So that's essentially what's happening for your hydrogen fuel cell. You need to remember how this is structured, because the cathode and the anode is a bit different than when you're looking at your electrolytic cell, your electrolysis. So for your chemical cell, your H plus is produced at your anode. Those electrons move around the circuit where it's added to oxygen, your ion, your H plus ion, and that's going to be forming your water. So that's your hydrogen fuel cell. Okay. Right, now for question 7. Question 7, this one is about iron. All right, so iron is a metal. We're going to describe how it actually conducts thermal energy. Right, and all metals have this lovely thing that allows it to transfer heat or energy. So we know that energy is transferred by the delocalized electrons. Right? So those are what transfers energy, thermal energy, through metals, through all metals. Iron is the same concept, right? Because if we have iron, let's say this is the iron rod, and we have these should be all touching. These are the positive ions. The electrons, right? They are delocalized. They're all the way between, right? Which means, therefore, that the heat being distributed from this electron can move from here and end up all the way over here, right, to transfer that heat. And that's why they're usually good conductors of heat and energy. Okay, so for 7.2, pure iron is too soft for many uses. It's going to explain why mixing iron with other metals, right, makes the alloy harder than pure metal. Okay, and this takes us back to these simple diagrams again, right? Because if we're drawing the diagram for pure metal, I know this is so key stage 3 in terms of these diagrams, but they're so helpful, right? So if we have pure metal, then we have a uniformed look, right? So they're in regular lattice in those rows. All of these are positive ions, by the way, right? So they're in regular rows, so which means that they will easily slide over each other. So if I hit here, it's just going to easily slide over, so it makes it very soft. But if I have an alloy, which means I've mixed it with other metals, or in some cases with a non-metal, okay, it means that it's not going to have that regular arrangement anymore. So that regular row that we're used to, it's no longer there. And if it's no longer there, it means that those metal ions sliding over each other, those positive metal ions that are sliding over each other, it's no longer there. So we have different size. So we have different size atoms in our alloy, right? So it means, therefore, so layers are distorted. And if layers are distorted, they cannot easily slide over each other, right? So layers do not easily slide over each other, right? Or easily slide. You don't even have to have the over each other, right? So because it no longer slides easily, it simply means that it is now going to be stronger. It's going to be harder, right? Those properties are going to be changing, right? So that's your pure metal and your alloy. Okay, so for this question, 7.3, when iron reacts with chlorine, right, so we're going to have 0.2 mole of iron and it reacts with 0.18 mole of chlorine, which is the correct equation for the reaction. So we're going to just use moles, really. So we have iron. Let's look at the iron to chlorine ratio, Cl2 ratio. So if we have this as 0.12 moles to 0.18 moles, right, we're going to try and see if we can get whole numbers. So divide this through by 0.12, which is the lowest number, 0.18. That's going to give a 1 to 1.5 ratio, but we don't want a 1.5, so we're going to have to try and make this into a whole number, really. So we can multiply all of this by 2, so that then is going to be in a 2 to 3 ratio. So we know we need 2 Fe to 3 Cl2 in our equation for this equation to be correct. So now let's find which one corresponds with this. So 2 Fe, 3 Cl2. So that means our answer is going to be that one there. Okay, so that's our response for that question. 7.4. Oh, this is a lovely question as well, right? So what is the ratio of the numbers of ions in Fe3O4? So we have the most common oxides, right? Those are Fe2O3 and Fe3O4. Now remember, a lot of these ions, they exist, they're out there, they're within compounds. So when you think about iron 2 plus, iron 3 plus, you sometimes you think about them in isolation, but they're there, they do form compounds. So this compound, a rule you need to remember about all compounds, they're all neutral. They're all neutral. So it means that their overall charge should be equal to 0. So when we're looking at something like this, the ions are in such a ratio where the charges are 0. Okay, so let's look at each of these. So we notice that only iron will be changing its oxidation state, its ion. So we have 4O2 minus, 4O2 minus, 4O2 minus for all of them. So we need to know the overall charge here is going to be 4,2, so that's going to be 8 minus charges. So in order for this to be neutral, 0, we must also have 8 positive charges. So now let's see which will actually give us 8 positive charges. So if we look at this, so we have 2 plus, so 2 is 4, so that's 4 plus 3 plus, that's going to give us 7 plus. That does not work, right? We're going to have a minus 1 charge remaining. And remember, ionic compounds, they usually have no overall charge, 0. Let's look at this one. So we have iron 2 plus, so that is 2 plus, and 2 iron 3 plus, so 2, 3, 6, so that's 6 plus. So in total, we have that 6, 7, 8, so that's 8 plus, right? So 8 plus, 8 minus. So my answer is going to be that balances out. Now, just to be sure, let's check the others to see. So 2, 3, so that's 6 plus, does not cancel out that 8 minus charge. And this is 3, 3 is 9 plus, does not cancel out. So our answer is definitely the second box, which indicate to us that we have 1 iron 2 plus, 2 iron 3 plus, and our 4 O2 minus. So that's going to be our answer for those ones, for that one. Okay? And the formula arises by counting the number of each that we have. So you might be wondering, how did we get Fe3, right? But remember, once we have balanced the charges when you're writing a formula, now it's just down to us to write the final formula. It's just us looking at the symbols. So if you look at this, we have 1 Fe there, 2 Fe there, so that's Fe3. And for our oxygen, or oxide, not oxygen, oxide, we have 4 of them. So that's the formula there. Okay, so that's question 7.4. Now question 7.5, this is a pretty simple one. It's the percentage by mass of iron in our iron oxide. So for this one, we're going to need the MR, right, which is the relative formula mass. Okay, so essentially we're doing this. We're doing our iron. So we have 3Fe, the mass of 3Fe divided by our Fe3O4, and then we're multiplying that by 100 to find the mass of iron in the entire compound. Okay, so let's find the MR first. So MR, so that's going to be 3 times 56 plus 4 times 16. So that's going to be giving us 232. And then we can find the percentage of iron, which is 3 times the 56 divided by 232. Then we multiply that by 100. And that's going to give us an answer of 72.4%. That's a percentage abundance. So within this entire compound, which is 100% of it, 72.4 of it is made up of iron only. Okay, so that's what that one is saying. Oh, this lovely 5 marker, not 6 marker, which is a calculation question as well. All right, so for this one, it's a reacting mass combined with volume question. So let's read through it. So iron oxide reacts with carbon to produce carbon dioxide. This is the equation. So this is the equation that we're doing. Calculate the volume of carbon dioxide. So questions like these, if you get an equation, it will usually tell you to calculate something for one of the species. So in this case, it's calculating the volume of carbon dioxide. So I always underline what I'm concerned with. So carbon dioxide at room temperature and pressure, that is produced from 40 kilograms of iron oxide, right? So it means therefore that we're only concerned with this and this. Everything else in that equation, you can just ignore, right? We do not want them. Even though it says we're using excess excess carbon. Remember, if we're using excess, it means that the iron oxide is the limiting reagent, which means that the proportion of carbon dioxide that is produced will be dependent on the iron oxide and not the excess carbon. So we can ignore that completely, right? So let me put it over here so I have more space. So I'm just going to write what I'm concerned with. So I'm concerned with 2Fe, 2O3, and I'm also concerned with the 3CO2. So those are the only things that I'm looking at for this. Okay, now the first thing I'm going to do, it gave me this value. So because it gave me this value, it means therefore that I'm going to be using it, right, as a first point of my calculation. And because on my line I do not have any kilograms down here, it means therefore I can actually convert my kilograms into grams, right? If the unit line suggested kilograms, I would have worked with kilograms, but it didn't. So I'm going to convert to grams. Okay. So first thing I'm going to do, I'm going to convert this. So my 40 kilograms is equal to 40,000 grams, right? So now I have that. Now I'm going to finish off my calculation. And in order for me to work with this reacting mass, I'm going to be finding the number of moles. So first thing I'm going to do, right? Find moles. So the moles of this, so N is equal to that 40,000. And I'm going to be dividing by the relative formula mass, which is given to me here, which is 160. So my number of mole is equal to 250. So that's my number of moles. Okay, that's the first thing I'm doing after conversion, of course. Okay, so now the second part, I'm going to be using mole ratio to find the moles of carbon dioxide. So I'm using the mole ratio not Russian, mole ratio, to find the moles of carbon dioxide. So I can see that it's in a mole ratio of 2 to 3. That's my mole ratio. So it means that this represents 2 moles. So I need to find what 3 moles would be. Okay, so mole of CO2, I'm going to be doing my 250 multiplied by my 3/2. Okay, and that's going to give me what 3 moles would be, and 3 moles is going to be 375 moles. So I know that that's the number of moles of carbon dioxide that is formed. Right, now the next bit of this, because I'm not done, it says I should calculate the volume of it, of that gas that is produced. So now I need to find the volume of that gas. In order for me to do that, I'm going to look at a key information that was given to me. And it says the volume of 1 mole of any gas at room temperature or pressure is 24 dm cube. And because this is already in dm cube, I do not need to do any conversion. I can just use 24 as is. So 1 mole is equivalent to 24. So I need to figure out what 375 moles would actually be. So volume of carbon dioxide, CO2. That's the third thing I'm going to be doing. So that's going to be my 375 multiplied by 24. And that's going to be giving me 9,000. So my answer is 9,000. So that's going to be my number of my volume of gas that is produced if I use 40 kilograms of my iron oxide with excess carbon. Okay, so usually the calculation for this remains practically the same, right? So once it's reacting masses, it will usually give you something that's asking you to calculate something for, and it will give you a bit of information about the other. So first thing you ought to do, figure out which 2 species is actually concerned with. Lay it out just like this. If you have any conversion to do that conversion. Then you find number of moles, use mole ratio to go to the other side to find the carbon or the other species. Once you're at the other species with the number of moles, then you can convert to your volume, your mass, or whatever that question actually asks you for. Okay, so this is general rule of how to do this question. Okay, now question number 8. Right, so this question is about propane. So this figure 7, it shows this displayed structural formula for propane. We're going to explain why propane has a low boiling point. Okay, and this takes you back to the lovely concept of structure and bonding. Okay, so let's look at this. So propane, we can see it's all covalent bonding. And there are 2 types of covalent structures. So we have the simple and we have the giants. Now this falls under the category of simple, right? So we know that propane is a simple molecule. And because it is a simple molecule, it is going to have weak intermolecular forces, right? So the intermolecular forces are weak, which requires little energy to overcome. And notice my use of language because it's explain question. I have my so in this case as opposed to because, right? So I'm explaining why that is so, okay? Why it has that low boiling point. So that is question 8.1. Question 8.2. Propane reacts with oxygen to produce carbon dioxide and water. This is exothermic in nature. right? So for exothermic, you know that if something is exothermic, energy is being released. Energy is released from the reaction. Right? So energy exits, it's released. Okay, and because of that, the product will have less energy than the reactant. So that's something that we know. So we have the reactant and the product is going to be less, right? Because we're releasing some energy. So we can eliminate these. These have products that have more energy, and that can't happen if we're releasing it. Okay, so now we're going to look at these two to figure out which it is, right? So we have the overall energy change from the product to the peak. That's dodgy. So we know that is the answer B is the correct answer for this one, where we have that energy change pointing from reactant to the product. And please pay attention to the direction of your energy change arrow, right? The energy is moving from where we were at the reactant to where it ended up at the product, right? Now let's move on to question 8. Let me take it. The answer is B. There we go. So question 8.3. So we have the displayed formula for this equation. It shows the reaction between the propane and oxygen. So we have that displayed formula. The overall energy change is exothermic, and we have this value here. Overall is exothermic. Now we're going to show the bond energies. So the table shows the bond energies. Sorry, I don't know what I was reading. Right, bond energies. So we can see each of these, but the C single bond H is actually missing. So we're going to calculate the bond energy for that one. Okay, so first, let's see if we can highlight. Is for the question like this, I love to use highlighters so I can see the bonds. Okay, so I have this. These are CH bonds. All right, let me highlight CH bonds. These are my CH. Do I have CH anywhere else? No, so I need another color, right? So I have my C single bond C, right? Those are there. I don't have any more C single bond C anywhere. So I can change my color again, right? So that's O double bond O. I have my C double bond O, C double bond O, and I have some OH as well. So I have my OH bond here. Those are OH bonds. Now, while we're doing this, ensure you're paying attention to the numbers that are in front of these, because they're going to be crucial when we're actually calculating these in order for us to tell which bonds are broken and which bonds are made. Okay, so let's carry on. Let's see how we can start doing our calculations. So our bonds broken and or bonds made. This is how I normally do it. If you do it differently and you can keep track of it, by all means, do it in the way that you feel comfortable doing it. Okay, so let's look at my bonds broken. So in this case, I know I'm going to break 2 of my C, single bond C. So that's going to be 2 times my 3, 4, 7. And I'm also going to have 8 of my C single bond H. So that's 8 times my C single bond H. I do not have a value for that, so I'm just going to leave it as that. And then I have 5 times my O double bond O, which is 498. Okay, so that's going to give me total of 3184 plus my 8. Let me just say X. Let me use this as X because I think it's easier. Let's just think about it as 8X. As 8X. All right. Now let's look at my bonds made. So for bonds made, I have 3, not 3 actually, but 6. Common error. I was going to make that error. So I have 2 of these. So it's 2 times 3. So that's 6 times my C double bond O, which is 805. So that's 6 times my C double bond O. And I have 8 times my OH bonds, my O single bond H. So that's going to be times my 464. Okay, so I have that. So the overall for this, if I should add all of these, I'm going to end up with 8542. Energy released is equal to bonds broken minus bonds made. We're going to fill in this information and then we rearrange to solve for X. So energy release, so that is negative 2219. Remember, it's exothermic, so negative number. That's going to be equal to bonds broken, which is that 3184 plus 8x. And we're going to minus 8542. And now we can try and solve for X. So that is going to be, 8x is equal to 3139, and then we solve for X. That's going to be 3139 divided by 8, and that's going to give us an answer of 392. So our answer is 392. Okay, now you should be able to rearrange that equation to solve for X, right? Since you're in triple, but just in case you're unsure how we got to this answer, I'll just put the rearrangement down here. So that is 8x is equal to negative 2219, right, minus 3184 plus 8542. Okay, so that's how we would have rearranged it to get that as our answer. Okay. All right, now let's move on to number 9. Number 9, so this question is about acids and their reactions. So this one is looking at strong and weak acids. So we know that it can either be one or the other where acids are concerned. So what is meant by a weak acid? So a weak acid, so this is where we're going to be using the ability to ionize either fully or partially. So our weak acid, so these are acids with weak, no, let me not use the word weak, which partially ionizes in aqueous solution. Right? Instead of ionize, you can say partially dissociates. Either of those are correct. Right? But for a question like this, mark point 2 depends on mark point 1. Which means if you mention something that's incorrect here for mark point 1, and you said in aqueous solution, you can't get that mark, either of those marks. Okay, so this is a classic case of mark point 2 dependent on mark point 1. So next question. So explain what happens to the pH of an acid as the acid is diluted with water. Okay, so based on the pH scale, right, ranging from 0, 1 to 14. So we know that if we are adding water to an acid, the pH is going to go in that direction. So which means that the pH increases, and it's explained because the concentration of H plus decreases. Okay, so remember, closer to this end, we have a greater amount of, or greater concentration. Let me not use the term amount, a greater concentration of H plus, right? So greater concentration of H plus here, right? And lower concentration as we move further to 7 and going into the alkali realm. Okay. Now for this one, so a student does a titration to find the volume of the acid needed to neutralize an alkali. The student fill the burette with acid. Give 3 more steps that the student must do before adding the acid to the alkali from the burette. You should name any equipment used. Okay, so it mentioned that the burette is going to have acid. So it means therefore that the next key equipment in titration will have the alkali, right? So use pipette to add the alkali, right? And it mentions ensure you name any equipment that is used. So that's what we're going to be using. So we're going to use the pipette to add the alkali, right, into a conical flask. All right, so we're going to add that into a conical flask, and then we're going to add indicator to the alkali. Right, now in this case, do not write this universal indicator. Do not, under any circumstances, write that. Right, it is not accepted because we do not use universal indicator in titration. So you can name an indicator, add phenolphthalein to it, right, add methyl orange, right? You can mention an indicator, but do not, under any circumstances, write universal indicator for a titration question. Okay. Now for the next one, so the student, let me change my color, ink. So the student titrated the solution containing 0.045 moles of sodium hydroxide with 0.1 molar or mole per dm cube hydrochloric acid. The reaction is based on this equation. Calculate the volume of hydrochloric acid, right, used in this. Okay, so we're concerned with sodium hydroxide and hydrochloric acid. So it mentioned that we have 0.0045 moles of my sodium hydroxide, and these are in a 1-to-1 mole ratio, which means that this is the same as that number of moles, just the same. So all I need to do is convert, well, not convert, but calculate the volume directly. I don't need to do much right now, really. Okay, so we're going to do volume is equal to number of moles divided by the concentration. So that number of moles is 0.0045, and we're dividing that by the concentration, which is 0.15. That will give you 0.03 dm cube. Remember, based on the unit, moles will cancel out, but the final answer will be in dm cube. Now we need to convert here from dm cube to centimeters cubed, and that's when you multiply by 1,000. Multiply by 1,000, and that will give you 30 centimeters cubed. Okay, so that's going to be our answer for that one. Okay, now the last question on this paper, right? So a calcium atom is larger than a magnesium atom. We're going to explain why calcium reacts more vigorously than magnesium, right, with hydrochloric acid of the same concentration, which means concentration of the acid stays exactly as is. We're just altering the metal that we're actually using. Okay, so this takes us back to reactivity. Reactivity down for metals. Change this color. For metals, once we're going down a group, right? So for metals, if we're going down a group, reactivity increases. Reactivity increases, right, due to ease of electron loss. Ease of electron loss. Okay, now when we think about it, the further away the electron is from the nucleus, it means therefore that those electrons are going to be lost quite easily, right? So period 2, period 3 have 3 shells, period 4 have 4 shells, period 5 have 5 shells, right? And so forth, okay? So it means that a metal that have this small a radius from the nucleus, it means therefore that it's not going to lose electron quite easily, right? Especially if you compare it to something that have this many shells, right? Means that the electron on this shell is feeling such little nuclear attraction. It means that the electron would just go somewhere else because it's not feeling that nuclear attraction as much as if it's in a closer shell, right? And that's what this question is about, right? So calcium outer shells are further from the nucleus. So the outer electrons are less strongly attracted to the nucleus. So positive ions are formed more readily. And that's the full extent of it. Okay, so think about your metals in the opposite sense of your non-metals. Metals, they need to be large, right? Electrons need to be far away, right? So it's not feeling that nuclear attraction so that it can be lost easily. That's when it's more reactive. But for non-metals want to gain those electrons. So they need to be very small so that the outer electron is feeling a lot of that nuclear attraction, so it can pull other electrons towards it. So that's essentially what's happening here. Right? It's just the size of the atom, and it impacts the reactivity. Right, now, thank you for listening to this video of me exploring this paper. Now, if there's any other question that you want me to go through, or something that might be tricky, or a topic that might be tricky and you want me to go through it for you, just pop it in the comment section and I will get on that. Thank you.